Okay. So seeing as most of you know me, I'll skip over this slide. Go to the overview. So I'll give a very basic introduction on laser doping, then talk about the benefits of using continuous wave laser doping for forming deep molten regions. Then a little bit of modelling the diffusion process within laser doped regions, laser doping from aluminium oxide dielectric layers, a method to contact buried layers within silicon solar cells, and then talk about some hydrogen passivation of laser-induced defects. So looking at laser doping, why do we do laser doping? Well, it's because the diffusion occurs in the liquid state, and that results in diffusion coefficients about 6 orders of magnitude higher than that in the solid state. So it means we can do diffusion processes in the matter of microseconds as opposed to minutes or hours. This was laser doping itself was first demonstrated in about 1968, so it's been widely used within the semiconductor industry, but very little in solar cells. There are a variety of approaches you can use for laser doping, such as using dopants already within the solar cell from ion implantation or a diffusion such as the phosphosilicate glass layer. And then you can use the laser to drive and redistribute those dopants within the solar cell. Another method which we typically use here is to apply a layer of spin-on dopants and then perform the laser doping process to incorporate the dopants into the solar cell. You can also use an ambient with a dopant source for gas immersion laser doping, or similarly laser chemical processing where you have a laser jet or laser which is guided by a jet of, say, phosphoric acid. But most of these processes end up with the same result. Now, one unfortunate problem which occurs with laser doping is the generation of defects. And these have typically hampered the performance of a lot of laser-doped solar cells. So looking at a standard laser-doped solar cell with a full area aluminium back surface field, until a few years ago, it was limiting the efficiencies to around 19%. Now, the defect generation is a complex process, and you could probably look at Ziv's thesis for a much better understanding of this. It can depend on a whole array of factors, such as the orientation of the silicon, the purity of dopant sources you're using, when you're using Q-switch lasers, the pulse energy, pulse repetition, and can also be influenced by the dielectric layers. So some methods to avoid performance degradation. One, you can do the laser doping before you put the dielectrics down, and that avoids some of the thermal expansion mismatch between the silicon and the dielectric layers, which can cause these defects to form. You can also use intermediate silicon dioxide layers underneath silicon nitride to hold the silicon under compression rather than tension to reduce defect formation. And you can also use continuous wave lasers, so that effectively only melts the silicon once during the laser doping process, so you don't have this repetitive melting and solidification of the silicon. Now, for the process we adopt here at UNSW, we typically perform the laser doping through a dielectric layer, and it is a self-aligned process. So we both incorporate dopants, diffuse them into the silicon, and open the dielectric layer locally, which we can then use to do light-induced plating, so it only plates to this laser-doped region, so a selective plating process. Now, for conventional laser doping processes, when you're using Q-switch lasers, the junction depth obtainable from the laser process is very much dependent on the duration of the laser pulse. So as you increase the pulse duration, you can actually form deeper molten regions because you can heat up the silicon without reaching the vaporization temperature. If you only have a very short pulse duration, you're very limited in the depth of silicon you can melt without leading to ablation of the silicon. So really what we want to do is go to a continuous wave lasers so that we can have the silicon molten for a time in the order of microseconds rather than nanoseconds like for conventional Q-switched lasers. So if we look at some of this continuous wave laser doping, we can form molten regions well over 10 microns deep. So we can get junction depths of basically a semicircular cross-sectional junction profile, which is well over 10 microns. And in this instance, the junction depth is very much dependent on the speed that you process the laser, and that determines the time that the silicon remains molten for and the time that the diffusion process occurs. Now we can also process very small contacts, so looking at developing point contacts. With a continuous wave laser, it's very difficult to do this. You either need very expensive and shutter mechanisms to be able to operate in the order of microseconds, or in this instance we use a physical mask which is aligned perpendicular to the direction of travel of the laser beam, which is scanning through deflection mirrors. And for this we can generate a point contact about 40 microns long, and it's only about 10 microns wide, and the junction depth here is still about 8 microns, so we can get sufficient doping for these small contacts. Now, for some of the conventional diffusion processes with laser doping, they report uniform dopant profiles. But for a lot of those, they're only talking about a melt depth of 10 to 100 nanometers. And if you look at the different conventional Gaussian curves, dependent on the effective diffusion length of the process, which is related to the diffusion coefficient and the time. As you increase the effective diffusion coefficient, you act to spread out the dopants more uniformly within the molten region. So if we go to a normalized graph, which is a ratio of the depth to the characteristic diffusion length, and the ratio of the dopant concentration at a given depth to that at the surface, we can see that up until we're basically a depth value equal to the characteristic diffusion length, we pretty much have a uniform dopant profile throughout that silicon up to the surface. As we increase this ratio further, so we go further into the silicon, that's when we start to see what you would expect from a typical Gaussian diffusion profile. So if we look at some of the SIMS profiles from a CW laser doping by varying the speed, we see that the faster speeds roughly look like a Gaussian diffusion profile, whereas the slower speed at 0.5 meters a second, we can see it's starting to look like more of the conventional box profile that you expect from short pulse length Q-switch lasers. And if we compare a process at 2 meters a second with a pure continuous wave laser in the black to a quasi-continuous wave laser in the red, and this operates at a repetition frequency of 80 megahertz, so you've got about 12.5 nanoseconds between each successive pulse, and it can result in a near continuous wave process. But you see subtle differences in the junction depth and this kink which occurs at about 3 microns depth, and we get a similar kind of kink for this laser doping with the CW laser at a slow speed. And this could be due to a number of things. One problem with doing SIMS measurements is we have a very small laser doped region, so typically we have to do multiple passes with the laser adjacent to each other to get an area large enough for the SIMS measurement. So we may be overlapping some of the silicate regions which have already been diffused, which could alter the diffusion profile. Now if we look at modelling the actual diffusion process, looking back at some of those profiles which roughly look like a Gaussian diffusion process, if we add in a pure Gaussian diffusion profile, it's a hypothetical, and this is to conserve the number of dopants in the diffused region, you can see that we're roughly, I've played around with the numbers, so we get roughly about the same surface concentration, same junction depth. But what you see is during these mid depths, the curves don't match, and the actual SIMS profile is always higher than that predicted by the model for all of the speeds. But as you go to the faster speeds, it becomes a closer representation. Now if we look at the difference between a quasi-continuous wave and a pure continuous wave laser, for the continuous wave case, it's the same graph as before. We've got this lower theoretically predicted value than the actual value. And if we look at the quasi-continuous wave case, if we assume that each pulse of the laser acts in isolation, so that the pulses of this laser are about 10 picoseconds, and for the laser doping process there's about 160 pulses supplied over the laser doped region. If we approximate that, it's clear that there's no match between the theoretical prediction and the quasi-continuous wave case. But what happens for such a high repetition frequency is that each pulse adds energy to what has been delivered by the previous pulse. So you don't get a complete resolidification of the silicon between successive pulses. So as you add more pulses, it can grow the molten region, and you can form these deep molten regions just like the continuous wave laser. Now, if we want to start to model this diffusion process, this is a hypothetical case where we've seeded a Gaussian diffusion profile from a depth of 5 microns, and we're taking a single time step of duration 2 microseconds, resulting in this diffusion profile here. Now, we've played around with the maths, and we've added 1,000 time steps into the model, and we've actually seeded Gaussian diffusion profiles from each depth element, which there are 1,000 different depth elements within this region. So at each point in time, we seed Gaussian diffusion profiles, and then for each depth, you have this little element of concentration caused by this diffusion process, and then we sum over all of those diffusion components for all the other elements of silicon, so that at each time step, then we get a new diffusion, an overall diffusion profile. And what we can see is that there's perfect agreement between taking it as a single time step or summing it over each individual component at each individual point in time. So if now we start to incorporate the influence of a solid-liquid interface, this black curve is just the calculated curve without any influence of the solid-liquid interface and without any conservation of the dopants, so that the dash profile would indicate where the dopant profile should be. So obviously we need a conservation of dopants within the molten silicon region. So we've applied 3 different model scenarios, A, B and C. For A, we use a symmetric linear scaling factor to just bump the diffusion coefficients, the diffusion concentrations upwards to have a conservation of dopants within the liquid silicon. For the second process, we use an asymmetric linear scaling factor, so that basically half of the diffusion or the dopants are going to the left and half are going to the right. And in the third, we've done a similar process, but in this case we have a constant amount going to each value of each depth location of silicon. And this is just to look at the different perturbations of the model to check the consistency. So what we find is that basically, no matter what we've done with the 3 different models, essentially the diffusion profile is the same. And it roughly approximates the case where we don't have any influence of the solid-liquid interface up until we're approaching this solid-liquid interface. And then you start to get a build-up of these dopants around this solid-liquid interface. So now, for the laser doping process, it's actually a time-dependent process. So we can approximate this laser dope region. We can assume that it's symmetrical in the XY direction, so that we've got this similar junction depth or melt depth in both directions. And this is extracted from EBIC of a whole different range of speeds. So we can assume that we can get a function of the actual the depth of the molten silicon as a function of the position along this axis. So then we can translate that into time as the laser is scanned over the surface of the laser. And then I've played around with the numbers a little bit. So we've added a depth factor to say that, well, look, this is going to be a rough shape of the molten silicon, but it could actually be deeper than where the EBIC signal is indicating the junction. And similar, we've added a time dilation factor to say that, well, look, we're doing multiple passes with the laser over a close region, and there's also uncertainty in the actual the dimensions of the laser beam. They have for the laser beam we're using, it has a spot size of about 20 microns at the 1/e squared radius, but that's not necessarily the size of laser or the molten silicon that we should be considering. So we've added that in. So if we start to look at the influence of the solid-liquid interface, taking again this Sims profile at 4 meters a second, if we have a conventional Gaussian diffusion profile without any influence of the solid-liquid interface over the same kind of time regimes, we don't have a junction depth as deep as what we would expect. Now, if we start to simulate the effects of a solid-liquid interface, and for this one, we actually have a depth factor of 0.8, so it's actually the depth of molten silicon that we've modelled is less than the junction depth of the e-beam signal, which is not practical, but it shows the influence that we've actually measuring or obtaining a junction depth by the model which is less than what we have from Sims. As we start to increase this depth factor, we see that it starts to approximate the case where you don't have any influence of the solid-liquid interface. But it's only until you have a depth factor of about 3 to 5 where you don't really have an influence of the solid-liquid interface in determining the diffusion profile. So if we take these Sims profiles again, if we don't have any influence of the solid-liquid interface, we see that we do indeed expect a deeper junction depth. But if we add this model, we see basically perfect agreement between the Sims profile and the model. And this was model A with the symmetric linear scaling factor. So we can see that this simple 1D model can effectively describe a lot of these laser doping processes. But it doesn't work for the case of 0.5 meters a second, which was a much deeper molten region and for a much longer period of time. So in this case, we don't get this characteristic kink described by the Sims profile. So what I've done here is I've tried a different regime where we have 3 successive pulses of and melting to different depths of the silicon. And you can sort of expect this as you do one pass. The next pass is shifted a little bit to the left or the right, and again for the following laser pass. So you wouldn't expect the same depth of molten silicon for each at a given location. And what you can see, it's certainly not a perfect fit, but it can start to describe this kink at these deeper molten regions of about 7 microns. So that could be a plausible, although not necessarily correct, explanation for this kink in the profile. And it may also be that we're starting to get into a regime where we could have processes like segregation occurring too. If we start to look at some partial solidification within the molten silicon region when we're using a quasi-continuous wave laser, if we don't have any influence of a solid-liquid interface, we'll actually be expecting junction depth of about 6 microns in comparison to about 4.5. So now if we take a single pulse, which this is the continuous wave case, and we expect a junction depth of still about 5.5 microns. Now, even though the time in between each pulse is very, very short for the continuous wave laser, like 12.5 nanoseconds, it's not unreasonable for us to assume that some of the silicon does actually re-solidify between successive pulses, and we would expect that the solidification is occurring towards the surface. So these deepest molten regions would be solidifying first before the next pulse arrives. So what I've done, I've assumed one effective or single effective pulse which has a different effective melt depth throughout this process, and this is just quite a large simplification to make it easier for the computational model. And what we can see is that it does allow a reasonably accurate description of the Sims profile, including this kink, about the 3 to 4 micrometers. So it would appear plausible that this kink is due to this partial solidification of silicon within the deepest molten regions for this continuous or quasi-continuous wave laser, which we don't see in the actual continuous wave case. Now if we look at laser doping from aluminium oxide layers, we can actually get very effective doping from dielectric layers even as thin as 10 nanometers using either ALD, so atomic layer deposition, or plasma enhanced chemical vapor deposition of aluminium oxide. And here you'll see the EBIC profile indicating the junction depth from this region. So in this case, which is a process speed of 2 meters a second, we have a relatively constant junction depth over the width of the opened region of several microns. As we go to the edge, it has this semicircular shape as occurs for the other dopant processes from the EBIC process I showed earlier. But there's an extra little kink in this cross-sectional profile at the very edges, and that would suggest that there's a second mechanism of diffusion taking place, and it may be that there's actually solid state diffusion occurring, which will have a diffusion coefficient many orders of magnitude lower than the solid state, to result in this this second part here. And one benefit of this is that even though our dielectric layer is only opened over this region here, we've got effective doping extending well beyond the opening in the dielectric layer, so that if we have any pinholes in the dielectric layer, this should help protect against recombination. And for some of the recent work I've done at IMEC, we've had up to a 35% utilisation of aluminium dopants within the aluminium oxide dopant source by using a processing speed of 1 meters a second, where we can get junction depths well over 5 microns, and we're approaching dopant concentrations of 10 to the 20 per cubic centimetre. If we're using a faster processing speed of 8 meters a second, we can still have a junction depth of about 3 microns. And this correlates to a rough throughput for this process with lines about 1 millimetre apart of around 100 megawatts. So it could be a very suitable process for commercial production. And these dopant densities in this laser dope region are much higher than what you expect with conventional aluminium back surface field, which is around 2 by 10 to the 18 per cubic centimetre due to the segregation during the epitaxial phase growth. So if you look at the contact formation using the aluminium oxide layers, we've been able to demonstrate contact openings down to 5 microns reliably in the dielectric layers. And so this is quite comparable with those contact features in the Pearl cell using photolithography. So we can see that we've got a highly industrially relevant process that we can have very, very narrow features without too many complicated optics from the laser. Now if we look at the effect on electrical performance, so lifetimes and implied VOC. Before annealing, so directly after laser doping, we see a large influence of the laser doping speed on the implied VOC. And particularly the highest speeds all saturated a value of about 640 millivolts. So we've caused a lot of defects in this laser dope region. The intermediate regions, we're still generating defects there, but some of the more effective doping in these regions can help protect against some of the recombination from this process. After we anneal the sample, we see that there's almost no change from these slow speeds. And that's because at very slow speeds you cause a lot of defects within the silicon, which I'll describe a little bit later. But for these faster speeds, we can recover up to about 50 millivolts of implied VOC through the passivation of those defects. So if we look at the actual lifetime curves after the annealing process, we see that for the slow speeds, we've induced a lot of bulk damage into the silicon. So you can tell that by the low lifetimes at low level injections. As we start to increase the speed, we increase this lifetime over all injection levels, but particularly at these low injection levels, by the time we're getting to 5 or 10 meters a second, we're starting to approach the case where we don't have any laser doping, which is the dots with the star. So we're not seeing any bulk damage remaining after the laser doping process. But we do have a lot of differences in the J naughts, which can be extracted from the slope of the curve in high injection. Now, we didn't really look into the effects of dielectric layers and the different dopant sources a lot, but from what we did, we saw a very, very large influence on how that interacts with the different processing speeds. So if we look at using a capping layer of silicon nitride, if we don't have any extra dopant source applied, so it's only utilising the aluminium oxide within the dielectric stack, we see that there's a relatively constant implied VOC, which is independent of speed for that dielectric stack, and when we don't apply any boron. If we suddenly add a boron dopant source, we see a very different trend emerging, and we've seen similar trends even without the aluminium oxide laser, where the highest implied VOC comes from having a very, very deep molten region, about 10 microns, and it decays as you go to higher processing speeds, which shortens the time that the silicon remains molten for, so it results in a shallower diffusion profile. If we go to the silicon dioxide capping layer, we see a very different trend than when we have silicon nitride capping layer. And in this instance, like the graph from the previous slide, we get the best results when we're going up towards 20 meters a second as a processing speed. And this can result in the silicon only remaining molten for about 1 to 2 microseconds, but that's still sufficient to get a junction depth of at least 1 to 2 microns. If we add in a boron dopant source, again, we get this highest implied VOC at 0.5 meters a second, similar to when we have silicon nitride capping layer. But then for higher processing speeds, we start to see this increase with the increasing processing speeds. Now for looking at some cell fabrication, we've added this into a IMEC iPerk structure, where on the left we have the cell with a conventional PERC cell process, so the local alloying of the aluminium back surface field. And on the front we have laser ablated contacts, so that's using a picosecond laser just to open the dielectric layer but not melt the silicon, so there's no substantial doping of the silicon. On the right we add this local doping from the aluminium oxide layers using the laser suitable to melt the silicon and incorporate the dopants from the dielectric layers. And otherwise all the other parameters in the wafers are the same. So if we have a look at the cell results, we can see that we're getting comparable cell efficiencies between the two processes. And we're getting a 20.4% efficiency average. There's a little bit of all of these VOCs are lower than expected. During this experiment there was some contamination in the aluminium sputtering source, but you'll see that the VOC of the pill cells with the aluminium oxide laser doping source is substantially lower than that using a conventional PERC cell process. And this can largely be attributed to the fact that these cells no longer have the firing process to form this aluminium back surface field, and that process is quite important from hydrogen passivation of defects within the bulk of the material. So we find that the VOC is substantially lower on those cells that don't have this peak firing process. But we can still obtain fill factors of towards 80%, and on our best cell as 20.7% efficiency, we've got a fill factor of about 80%. So we know that this contact structure does actually work and could be feasible for commercial solar cells. And from other work where we incorporated the laser doped selective emitter onto the front surface, so employing local laser doping onto the front surface to form a selective emitter, we had about a 0.4% efficiency gain. So if we were to incorporate that into this cell process, we'd be expecting at the first approximation somewhere around 21%. And from increasing the bulk lifetime of the material through perhaps adding this firing process back into the sequence to help release this hydrogen from the dielectric layers to passivate bulk defects, we could be looking at increasing the VOC towards say 680 millivolts and leading to further increases in the current density. And we could be looking at the high 21% for efficiency. Now if we look at a method to contact the buried layers in silicon solar cells, there's a lot of advanced solar cell structures which have very complicated processing in order to contact a layer in the solar cell which would otherwise be under another layer. And this often requires masking for diffusion steps or etching, and it often requires multiple diffusion steps in order to achieve these structures. So if we take the perf solar cell, so the passivated emitter with rear floating junction solar cell, on the rear surface we have a phosphorus diffusion over the majority of the area of the rear surface, but we have this local heavily doped boron diffused region just where we have the p-type contacts. So for this solar cell, they have a mass diffusion process to put the phosphorus diffusion over most of the area, apart from this region where they'll have this subsequent boron diffusion, and they have to make sure that there's a gap around this boron diffused region to avoid any tunneling between the heavily doped N+ and P+ regions. If we take a different technology, which is the buried emitter solar cell, so it's an IBC solar cell where essentially they do a full area emitter diffusion, but this is patterned in prior to the diffusion to stop the diffusion occurring in localized regions which will subsequently form the base contacts. And then they do the opposite diffusion, again requiring a mass diffusion process so that they can locally define where these diffused regions go. And during the second diffusion process, it actually pushes the emitter further into the solar cell. If we look at the sun power structure, we do a full area diffusion for typically the boron diffusion first. Then some of the regions are etched off to remove the diffusion and create a layer, a height difference in the solar cell, which can be used for a self-aligned metallization scheme. But again, this requires etching and diffusion masking for opening of the contacts, etc. And it's a similar case for the CSG technology, where they have these dimples and craters, and they remove substances or locally to contact layers underneath. So what we want to do is looking at using a laser to do some of this process, and particularly if we can do it in a self-aligned process in a single processing step. And then hopefully we can avoid the need to do some of these multiple thermal diffusions. So if, for example, we take a silicon wafer with an emitter diffusion and a dielectric layer, we add the dopant source on, then we illuminate it with the laser. Throughout the laser process, we start to expand the molten region, and it can become, as we've shown, up to about 10 microns depth. So you can redistribute dopants within this emitter so that they're relatively low in concentration, whilst simultaneously incorporating a high concentration of dopants, the same polarity as the base. And what that can result in is a compensated base type doping contact in a self-aligned process. Now, to demonstrate this, we've looked at EBIC. So that here we can see on a bulk p-type silicon wafer, we've got our conventional EBIC signal from the phosphorus diffusion, but there's no EBIC signal in the laser doped region. So we can see we've converted the initial N-type surface region into a p-type laser doped region. And this was through an industrial emitter of about 120 ohms, so it's a relatively heavy diffusion to be able to penetrate through. So what this means is we could potentially be looking at back contact solar cells on p-type wafers, or potentially on n-type wafers as well, with a single thermal diffusion. And you don't actually need to remove any diffusion or perform masking processes for this diffusion process. But it would still require alignment steps for the metallization process and the different laser doping processes between the N-type and P-type contact polarities. And also one of our colleagues, Catherine Chan, has demonstrated 14.5% efficiency on some of these initial test structures. But it doesn't always work out to plan. You can actually form transistors depending on the processing speeds used, and also the diffusion profiles of the emitter initially in the wafer, or potentially from the dopant source applied. So if we start to increase the speed, we can see that we're still converting a lot of the laser doped region to p-type silicon, but we have these n-type regions protruding into the bulk silicon region. And so we have a localized NPN structure around these peripheral regions. But in this instance, we still have direct contact from the p-type, heavily doped p-type laser doped region to the p-type bulk. As we increase that, we can have the case where we completely isolate the p-type laser doped region from the p-type silicon underneath. So we've got this n-type region basically all surrounding this this laser doped p-type region. So that may not be desirable for contacting solar cells. And in some instances you can keep this n-type diffused region, and you don't actually have enough dopants in the, or p-type dopants being added during the laser doping process to completely compensate the silicon. So we still have this n-type region of silicon, which has now been extended into the silicon a bit more, and it's of much lower effective dopant concentration. But if we play around with the actual, in this case, the phosphorus diffusion, so going to a much lighter phosphorus diffusion, so there's less phosphorus dopants in the silicon that we have to compensate. And this process was done at 5 meters a second. And what we can see, we've formed a local transistor. So we've got this p-type surface region, this n-type emitter, which is pushed down further, just like in the buried the buried emitter solar cell. And we still have this the p-type silicon base. So we can locally form transistors using this laser doping process. Now, if we talk on to one of my more familiar topics of hydrogen passivation. So we're looking at passivating some of these laser-induced defects, like you briefly mentioned on a couple of slides ago. Some of the defects that form during laser doping, particularly with the continuous wave lasers, are substantially large voids. These can be up to about 5 microns in diameter and be well below the silicon surface. So in this instance, we'd be looking at having a junction depth of around 10 to 11 microns. And we've got voids occurring throughout the silicon, or the laser doped region. As you change the speed, you start to change the size of these voids, and also where they occur in the laser doped region. So as you increase the speed, they typically they sit just below the silicon surface, and as you increase the speed, they get smaller and smaller. And you can still see them at processing speeds up to 5 or 10 meters a second, particularly around the edge of the laser doped region. And that could be a cause of concern in terms of if there's gases in these voids during the laser doping process, if that can cause these pinholes to form in the dielectric layers. We can also get cracks forming during the laser doping process. So for this sample on the left, it's been processed at 0.1 meters a second, which causes these crystallographic defects to form in the laser doped region. And it's unclear whether all of the defects formed during the actual laser doping process, or they were formed during the cleaving process perpendicular to the laser doped region. But over a large number of samples, we've been able to see that these cracks are particularly confined to this laser doped region, so that certainly in the laser doping process, we're causing a certain amount of stress in the silicon to allow these cracks to form. And certainly we don't want those on our solar cell for making contacts, because some of these cracks can extend well beyond the diffused region, so they'll be in the bulk silicon. If we go to very slow speeds, looking at 0.01 meters a second, we can have cracks forming in a zigzag along the laser doped region, and they can extend about 40 to 50 microns beyond the opening in the dielectric layer. And we can also have the case where we have cracks forming across the laser doped region along the edge, or some instances, although I haven't shown here, the cracks are going straight up and down the middle of the laser doped region. So in most of our experiments, we try to avoid these really slow processing speed because of how many defects they form and the limited availability of hydrogen to passivate some of these defects. We can also get these pinholes in the dielectric layer. So in the middle here, you'll see the voids, which typically around 0.5 meters a second looks like a sort of a footprint pattern up the middle of the laser doped line. But we also have these small pinholes in the dielectric layer, and you can see them again here occurring in the peaks of the pyramids and sometimes the base. And that could be due to the coupling of the laser illumination around these different features with the surface of the solar cell, causing these defects to form. So if we look at a conventional laser doped solar cell, so a full area aluminium back surface field, we take a PL image. So this has got the rear electrode already formed and silicon nitride on the front surface. And we just have to do the laser doping and the metallization process. So we can see a relatively uniform implied VOC around the 640 millivolt mark. As we do a laser doping process, and we've confined it to about a 5-inch region over a 6-inch cell, so you can see the difference that we're not altering any of the surrounding region with the laser doping process, but we are inducing a lot of damage into the finger region, and particularly in the bus bar, which has a high density of laser doped lines, so a high density of laser induced defects. If we do a short thermal anneal, about 400 degrees, 1 to 2 minutes, and this can be either in nitrogen or oxygen ambient, and this is just using hydrogen released from the silicon nitride layer during the formation of the aluminium back surface field. And what we see is that the recombination properties of the laser-induced defects are pretty much gone. You can only really see the effect in the bus bar, which has a much higher density to start with, but that may also the remaining influence on the implied VOC may be due to a higher J0 for the dark saturation current density contributions coming from this heavily doped region. And another way we can do this is we can actually incorporate this passivation process into nickel sintering. And that's typically around the 350 degree to 400 degree mark. So it can be effective at passivating these defects. So we don't necessarily need to do a dedicated process to passivate these defects. So if you look at the difference in the electrical performance of these solar cells, we see that the JSCs are pretty much similar, but we see a substantial increase in VOC of about 10 millivolts. We also see an increase in the fill factor and pseudo fill factor around the 0.4 to 0.5% absolute, and a 0.3 to 0.4% increase in the efficiency of the solar cells. So we can see the importance of passivating these laser-induced defects, even for a solar cell that only has an efficiency of mid 18%. So now to confirm some of the passivation of the defects, we've fabricated some test structures. So a P-type wafer with a symmetrical 100 ohm per square, 120 ohm per squared phosphorus emitter on both sides, and we've passivated by silicon oxynitride, which comes with the benefit of hydrogen. So before the annealing process, we have an implied VOC of 648 millivolts, a J0 of the whole structure, which is the diffusion of both surfaces and the corresponding surface passivation of 140 femtoamps per square centimetre, and the bulk lifetime's about 130 microseconds. If we do an annealing process, we can see that we can increase the implied VOC bulk lifetime, and we get a substantial reduction in the J0 from an improved surface passivation of the layer. So now we're looking at about 15 femtoamps per square centimetre per side for this solar cell. We then do the laser doping process, and we see instantly that we've reduced the bulk lifetime of the solar cell quite substantially through these generation of the defects, which can extend into the bulk of the device. We've also added a little bit of J0 from the increased doping in the laser dope region, and all of this results in a substantial reduction in the implied VOC at 1 sun. If we then do the same annealing process after the laser doping process, we can recover most of the damage we've induced during the laser doping process in terms of implied VOC, the bulk lifetime, and we again can get a slight passivation around the surfaces to reduce the total J0. Now, if we're starting to look at higher voltage test structures or more efficient solar cells that have higher VOCs, we would expect that the effects of the laser induced defects will be more important and could have further limitations on the performance of these solar cells. So we've got some P-type solar cells up until the end of silicon nitride on the front and rear, and these are sitting up around 700 millivolts. We then do a hydrogenation process to passivate bulk defects in the wafer, and in this case we don't see much of a difference in the solar cell before and after, because we've added extra measures to enhance the hydrogen passivation during the silicon nitride deposition process. If we add the laser doping of the P-type and N-type polarities, we see a substantial reduction in implied VOC. And the top and bottom cells have different laser processes with different densities of laser doped lines. So the sample on the bottom has a higher density of laser doped contacts, so a much lower implied VOC. As we again apply the same hydrogen passivation process, we can see that we're recovering a lot of this damage we've caused during the laser doping process and recovering towards about 40 millivolts in implied VOC. And that could be around, say, 1% absolute of these efficiencies in the solar cells of what we've measured so far. So some of the work I've done at IMEC was on the NPERT technology, so using a N-type wafer with a rear boron emitter. And so we're starting from the implied VOC after the anneal process of around 710 millivolts. As we introduce laser defects onto the front surface, so it's a selective front surface field in this instance, we see that we've caused a substantial reduction in implied VOC, particularly around the bus bar regions, which have a very high density of laser doped lines in this case, resulting in the complete opening of the dielectric layer over about a 1 millimeter width. As we apply an anneal process, we can recover a lot of that damage, resulting in about 15 millivolt increase in implied VOC. But again, you'll see that the actual implied VOC is still limited in the bus bar regions due to the remaining laser-induced defects. So if we start to look at the passivation of those defects, we'll see that without the anneal, we have a very low actual VOC on finished devices, below 650 millivolts. If we then sinter using the IMEC standard sintering process, which is a temperature much lower than what we use at, we only get a 4 millivolt increase in the VOC of the cells. And on another sample with a different finger pitch, we can take what had already had their standard sintering process, we can re-sinter it at an elevated temperature of 400 degrees, and we see that we get another increase of about 4 millivolts. So we're getting an improved passivation of these laser-induced defects through this high temperature sintering process. Now for the samples over here, we have a dedicated annealing process which was at 450 degrees in the belt furnace in oxygen ambient. We can see that we're having much higher VOCs on the finished devices, about 15 to 20 millivolts higher than cells which don't have any dedicated annealing process. And importantly, we can see that the VOC is stable through the subsequent sintering process, so that these defects aren't being reactivated during these subsequent thermal processes. So looking at the effect on the cell performance, what we'll see is roughly about a 0.7% efficiency enhancement just through the passivation of these laser-induced defects. So getting up to around 20.5% efficiency, and the best cells in this batch were about 20.7. But some of our more recent work, we've been able to show efficiencies over 21% on large area devices through this passivation of the laser-induced defects. And also we're getting this substantial increase in current over some of their conventional cells, and we seem to be able to passivate the rear surface of the solar cell and the bulk of the solar cell much more effectively using just the hydrogen released from the dielectric layers rather than using forming gas ambient, and in a much shorter process. And that's it. Thanks.